Hello, this is Pat Hindle, Technical Editor at Microwave Journal. It's my pleasure to welcome you all to this session in our Technical Education webinar series on VCO Fundamentals. Before we start, there's a few items that I'd like to bring to the attention of our viewers. Today's presentation is approximately 45 minutes long, after which time we'll hold a 15-minute question and answer session with our presenter. You may submit a question through the website at any time during the presentation through the Q&A box. The questions will be answered at the end of the presentation, and please address all your questions to all presenters in the Q&A box, which is the default setting. This presentation will be archived and available for viewing later on in the events section of the Microwave Journal website. Also, if anyone would like to see more details in the slides, simply click on the enlarge button in the lower left-hand corner. Our sponsor today is Mini Circuits, who provides RF, IF, and microwave products from DC to 40 gigahertz. While Mini Circuits is headquartered in Brooklyn, New York, they have design centers around the world. Their core technologies include core and wire, microstrip, LTCC, and semiconductors. They have more than 10,000 active products with more than 20,000 customers. They meet the highest quality environmental standards to deliver high-performance products. Mini Circuits has a very broad product offering, including 28 product lines, covering almost any type of active or passive product that you need. These include the VCOs covered here today. Mini Circuits has more than 800 catalog VCO models, ranging from 12 megahertz to 6.8 gigahertz, with hundreds more ready for fast turnaround. All are available for rapid customization, covering 3 megahertz to 7.1 gigahertz. They have a wide variety of frequency ranges, performance specification, and package types. At minicircuits.com, you can search for millions of live test data points from thousands of products to meet or exceed your performance requirements. The search engine includes standard and custom products, including those under development. A wide variety of component types are included to meet your needs. Visit minicircuits.com to find out more. Today's speaker is Dr. John McNeill. Dr. McNeill received his bachelor's degree from Dartmouth College in 1983, a master's in science from the University of Rochester in 1991, and a PhD from Boston University in 1994. From 1983 to 1990, he worked in the industry in the design of high-speed, high-resolution analog-to-digital converters and low-noise interface electronics used in high-speed, wide dynamic range imaging systems. Since 1994, he has been with the Electrical and Computer Engineering Department of Worcester Polytechnic Institute, where in 1999 he received WPI's campus-wide award for outstanding teaching. His research interests are in the area of analog and mixed signal integrated circuit design for phase lock loop, analog to digital converter, and instrumentation applications. At this point, I'll hand the presentation off to our presenter, Dr. McNeill.
Thank you very much, Pat. Good day, everyone. Welcome to the presentation on VCO Fundamentals. Again, my name is John McNeill from WPI, Worcester Polytechnic Institute. My email is listed here. If anyone has questions they think of later on after the presentation, feel free to contact me. Here is an overview of what we'll be talking about today. First, just the functional block concept of the VCO. We'll review some fundamentals on oscillators in general and look at some basic performance metrics. For the voltage-controlled oscillator, we'll look at different methods of tuning and then some advanced performance metrics, followed by a conclusion. So looking first at applications and specifications for the voltage-controlled oscillator, the functional block concept is shown here. The output of the VCO ideally is a sine wave in time. In the frequency domain, it's an ideal impulse at the oscillating frequency f osc. And the distinguishing feature of the VCO is the tuning input. So if we plot the oscillation frequency as a function of this tuning voltage, ideally we would see a linear characteristic covering some range of frequencies. And the performance metrics we'll look at basically describe how closely any real VCO meets this performance ideal. So typical applications for the VCO, one would be in an RF communications system where the signal of interest I'm looking at in the RF band is a particular range of frequencies, and a mixer, in this case an I and Q mixer, is used to down-convert the RF energy from some higher frequency range down to the intermediate frequency range. The local oscillator is mixed with the RF signal, and by choosing different frequencies of the local oscillator, I'm able to select different bands in the RF spectrum to convert down to IF. And having a voltage-controlled oscillator allows electrically tunable selection of the band of interest. VCOs can also be used in digital system applications. In this case, the output of my VCO is a square wave. In the phase lock loop application shown here, the phase detector compares the phase of the input at this frequency Fin to the phase of a clock that's fed back from this divide by n counter. If we look at the example of a divide by 2 counter in the feedback, then whatever our output frequency is here, by the time it's fed back from the divider, we'll have half the frequency. Okay. The phase lock loop looks at the phase difference produced by this phase detector, filters it, and tunes the VCO until Fin and this divided clock in the feedback are equal. It's a negative feedback system. And when the loop is locked, these two frequencies and phases at the input are equal. Well, if I've done that, then the output frequency must be equal to 2 times the input frequency. And this allows me to generate a higher frequency clock at the output of the VCO, but still locked to this lower frequency input clock. And this is called clock synthesis or frequency multiplication. So there are a couple applications for voltage-controlled oscillator. And if you look at the spec sheets, the specifications that describe VCOs, a lot of different specifications. This is a sample page from the Mini Circuits website, and as you can see here, there are a lot of different specifications. Depending on the application you're concerned with, some of these will be important, some may not. We'll cover the major ones today. First, we'll look at a general review of oscillator design. How do you control frequency? How do you control amplitude? And how you achieve these functions in different types of oscillators. So the different types of oscillators we'll look at briefly, the multivibrator, ring oscillator, resonant oscillator, and feedback oscillator. For each of these, the basic factors in oscillator design are controlling the frequency, determining the amplitude and output power, and making sure the oscillator starts up when power is turned on. The first we'll look at is the multivibrator, and the distinguishing characteristic of the multivibrator is that it has a single energy storage element, in this case a capacitor. So it's a first-order oscillator, if you will, and it's also called an astable or a relaxation oscillator. In this case, we're showing a current, plus or minus reference current, charging and discharging this capacitor between a plus and minus reference voltage. That's going to give us an oscillator frequency proportional to the current and inversely proportional to the CV-ref product. So one example of a multivibrator implementation would be a Schmitt trigger or some kind of bistable circuit that determines the plus and minus VREF function as the oscillator ramps towards one of these thresholds. Crossing the threshold causes the charging and discharging current to change sign, so we end up ramping from one threshold to the other. So the frequency is determined by the charging current, the capacitor value, and the VREF thresholds. Amplitude is controlled by the thresholds and the logic swing at the output of this bistable element. Startup is guaranteed. There's no stable state for this circuit, so whichever direction we happen to power up in will ramp to that threshold and go the other way. The second type of oscillator we'll look at is the ring oscillator. In this case, I've got N stages of logic inverter. And again, this is guaranteed to start up. There's no stable state. If we look at logic signal A, for example, a positive transition on the logic A output propagates to a falling transition on the B output sometime later, equal to the propagation delay of the logic gate, TPD. And then the edge continues propagating around the loop, and as long as I have an odd number of stages with a net inversion around the loop, that edge will just keep running around, and after 2 trips around the loop, I'll have a complete cycle. So the oscillation frequency is determined by the number of stages and the propagation delay. Okay. So again, the startup is guaranteed. There's no stable state for this system. Amplitude is controlled by the logic swing, and frequency is determined by the gate delay. For RF-type applications, typically a higher quality oscillator is needed. The resonant oscillator is used most often, and here we're looking at the concept of a natural oscillation frequency of resonance back and forth between 2 storage modes. In an LC oscillator, the 2 energy storage modes are the magnetic field energy in the inductor and the electric field energy in the capacitor, which naturally gives us a sinusoidal oscillation shape. The oscillation frequency given by the resonant frequency of this LC circuit, which is 1 over 2 pi square root LC. So to look at a slightly more intuitive view of the resonant oscillator, if we consider a mechanical analogy, this playground swing, here's somebody sitting on the swing, and we'll look at the angle that the swing makes with the vertical. Okay. When the swing is at its highest point, all of the energy in the system is in the form of potential energy. And if we release the person on the swing, they'll swing down through the phi angle equals 0 position. And at that point, they're at the maximum velocity, so we reach maximum kinetic energy. So the 2 energy storage modes are potential and kinetic energy. Swinging through the 0 angle to the extreme the other way, again, gives us a point where now we've reached maximum potential energy and minimum kinetic energy. So at the peaks of the angle, all the energy is in potential energy, and we've got 0 kinetic energy. Conversely, going through 0 angle, we've got maximum kinetic energy and 0 potential energy. So in this case, the frequency is controlled by the length of the pendulum, by the length of the swing, and also by the gravitational constant G in the case of this mechanical system. The amplitude is controlled by the initial position, the amount of energy we load the system up with at time t equals 0. And for this oscillator to start up, we do need some initial condition, some kind of energy input. Now, this is the case for an ideal oscillator. In the case of a real oscillator, if the person is not continually feeding energy into the system, due to frictional losses and wind resistance, we'll see the amplitude decline with time. Okay. And eventually, all the energy is turned from potential and kinetic energy into heat energy, and the amplitude decays towards 0. So on the playground swing, you can pump your legs back and forth to feed energy into the system. to maintain the amplitude. And the amplitude needs to be controlled by some kind of supervisory function. If the amplitude is decaying, feed more energy into the system. If you're swinging too high, feed a little less in. But you need some form of external supervision to determine the amplitude. So looking at the ideal LC resonant oscillator, where the energy storage modes are the magnetic field from the inductor current and the electric field from the capacitor voltage, frequency is controlled by LC. The amplitude is controlled by the initial condition. And we need some initial energy input, either in the form of an initial value for the capacitor or an initial current in the inductor. For the ideal case, the amplitudes stay constant over time. In reality, any resonance is going to have losses, ohmic losses in the inductor copper. If there's a core material in the inductor, that'll have losses as well, dielectric losses in the capacitor. So these non-idealities in the inductor and the capacitor, we can model those as this loss element, R loss, and that explains why the resonance is going to eventually die away. And in this case, the resistor heating models the change in energy from the organized energy of the electric field and the magnetic field to the random thermal energy of resistor heating. So the amplitude will decay towards zero in the case of any real resonant oscillator unless we somehow feed some energy in. So one way to feed energy in is by synthesizing a negative resistance function that provides energy input to the oscillator. And this, if R negative in the negative resistance is the same magnitude as the R loss, will exactly cancel the energy lost here, and we can make the oscillation continue indefinitely. The negative resistance can be synthesized with an amplifier and positive feedback. It's shown here in the case of an op-amp. If we look at the impedance looking into this node, applying a test source Vx, and looking at the current that flows in, the input resistance will be equal to Vx over Ix. If I apply Vx to this point with a non-inverting gain of 2 in this amplifier, I'm going to have 2 Vx at the output of this amplifier. I've got Vx here, so the voltage drop on this resistance is equal to Vx, but it's plus to minus this way. So I'm going to have a current flowing out of this node equal to Vx over R. Okay. So looking at this node, Ix is equal to minus Vx over R. So Vx over Ix is equal to minus R. So looking into this node, I can synthesize a negative resistance function, and the amplifier will end up feeding energy into the resonator. So this will counteract the losses in the real resonator. Another type of oscillator, the feedback oscillator, which is used at lower frequencies, for example, audio frequencies, the Wien bridge oscillator, I think illustrates another way of looking at the concept of oscillation that's very helpful. So the Wien bridge schematic is usually shown in this form with a bridge of RC on one side and a resistive divider on the other side. If we redraw it in this form to show the feedback a little more explicitly, we've got a gain A, a forward gain A in this direction, R1 plus R2 over R1, just a non-inverting gain of this amplifier. And in the feedback, we've got a transfer function, a frequency-dependent feedback factor beta. And if you look at this transfer function, the maximum magnitude you're ever going to see in the feedback to point P from the output is equal to 1/3. And at that maximum frequency, the phase of the feedback path is 0. And we're going to choose this frequency to be the oscillation frequency of the Wien bridge oscillator. And the way we're going to see that is do a little thought experiment where we imagine looking at this loop, breaking it here, injecting a test signal, and seeing how much feeds back to point P. So here we are, and we're going to assume that we've got everything balanced just right, so the A beta product is equal to 1. So I'm going to connect this switch over here, my 1-volt sine wave, and I'm going to set it to my oscillation frequency, FOSC, determined by this transfer function. And if I come in with a 1-volt peak sine wave at the input at Vx, to exactly make A beta equal to 1, I must have a gain of 3 from input to output to just make up for this feedback factor of 1/3. So I'll have a 3-volt sine wave at V out. Looking at the feedback through this transfer function at this frequency, I've got a gain of 1/3 and a phase shift of 0. So this sine wave will come back around the loop at Vp equal to 1 volt and in phase with the input that I'm providing. Okay. So 1-volt sine wave here at F-OSC produces a 1-volt sine wave here at F-OSC. So if I flip this switch over, I've got a self-consistent waveform that continues propagating around the loop, and if I've balanced everything just right, this will go on forever at a constant amplitude. So by having this self-consistent behavior around the loop, the oscillator will sustain its amplitude. What happens if I'm a little bit low on my loop gain? So here I've got A beta equal to 0.99. Well, in that case, putting in my 1-volt sine wave here is only going to give me 2.97 volts when I get to the output of the op amp, and fed back here 0.99 volts peak for my sine wave. So this is not enough to sustain oscillations. When I flip this switch over, the 0.99 goes around the loop to become 0.98, and the oscillation will decay away. On the other hand, if I get a little too aggressive, when I put 1 volt in here, now I'm going to get something a little bit larger out here, 3.03 volts, feeding back through the network. I'm going to get 1.01 volts peak, and when I flip the switch over, the waveform will get a little bigger every time. Until I eventually clip. And the amplitude will grow exponentially. In the case of the decaying oscillation, it'll decay exponentially. But if I don't have that loop gain exactly equal to unity, I'm not going to have a self-sustaining, consistent oscillation. So the way we're going to make this feedback oscillator work is similar to the LC oscillator in that we'll have some kind of supervisory circuit that's monitoring V out and then adjusting the gain of the A stage with some kind of adjustable gain function. So the supervisory circuit will adjust the gain by adjusting the value of R1 to exactly meet this A beta equals 1 condition. And if we design this circuit to have gain greater than 1 for amplitudes less than the amplitude of interest, it will start up just from random noise. The supervisory circuit will begin with a loop gain greater than 1, and then the amplitude will start growing based just on random noise until reaching the target amplitude that this supervisory circuit is looking for. Similarly, for the resonant oscillator, we've got to balance the negative resistance with the loss resistance exactly. If the negative resistance is too small, we're not feeding enough energy in, and the amplitude will decay away. If the negative resistance is too large, the amplitude will grow exponentially until clipping. The ideal case of unity loop gain, the R loss and R neg just being equal in magnitude and opposite in sign, is shown here. In practice, rather than a supervisory circuit, very often we'll just let amplitude grow until soft clipping occurs, and we'll let that limit the loop gain, and we'll get a self-consistent oscillation that way. The price we pay is there will be some harmonic distortion from this clipping, but we will stabilize the amplitude. At RF frequencies, the Clapp oscillator is widely used as a voltage-controlled oscillator, and the circuit is shown here. The Resonator is the LC circuit shown here. Okay. And to make up for losses in the Resonator, we need some gain and feedback. So the transistor here provides the gain. C1 and C2 are the feedback network. Okay. R is provided for DC bias. And the power and DC bias are in the collector of the device. And the output is taken from the collector, typically. And there's the load we're driving. Okay. Analysis of the circuit shows that the oscillation frequency follows the 1 over 2 pi root LC resonance expression for the LC oscillator, where the capacitance is the equivalent capacitance of C1, C2, and C3 in series. So the oscillation frequency is going to be set by this relationship. A more detailed view of the Clapp oscillator is shown here. Again, the DC bias in the collector. And the emitter of the device. At RF frequencies, the chokes are open, and the equivalent circuit is shown here. If we look at the equivalent impedance seen by the resonator, we can determine if we have enough gain and enough negative resistance to get the oscillation at the FOSC that we're looking for. So the analysis of the small signal equivalent circuit shown here gives us this expression for ZEQ, the equivalent impedance looking in. And we see that the impedance looking in has these capacitive components, and that feeds into that expression for the oscillation frequency. And this term here with the minus sign in front is the negative resistance. So the equivalent circuit looking in at the oscillation frequency is shown here. Typically what is done in the design, rather than having a supervisory circuit, we design to make sure that R neg is greater than R loss by choosing the C1, C2 feedback, and then we just let the soft clipping of the transistor transconductance limit the amplitude. So we'll be sure our neg is greater than the losses. That guarantees that we'll start up, and that choice can be ensured with the C1, C2 for feedback, and then amplitude will grow until the soft clipping of the transistor's transconductance limits the amplitude. So to summarize the different types of oscillators that are available, shown here, improved phase noise on the vertical axis and the frequency of oscillation on the horizontal axis. The feedback and multivibrator oscillators are typically used at lower frequencies where modest phase noise performance is needed. Ring oscillators work at very high frequencies, but for the best phase noise performance at high frequencies, resonant oscillators are what are needed. So we'll spend the rest of the presentation looking at the performance metrics for resonant VCOs. So the first basic performance metrics we'll look at are frequency range and tuning range. So going back to the page from the data sheet or from the catalog that we saw earlier, we'll look at an example of the one particular VCO operating from a range of 500 megahertz to 1 gigahertz. And here we are with the data sheet, this from the data sheet of the JTOS 1000W oscillator. So the first metrics we'll look at, the frequency range. This oscillator can go from 500 megahertz to 1 gigahertz. The operating power that it requires, 12-volt supply, and will draw 25 milliamps. Note that the voltage we use for tuning this may actually exceed the VCC available. So depending on the constraints in the system you're designing, to achieve the full range of the tuning for the VCO, you may need to exceed the power supply, and we'll see why we want to do that later on. And the power output available in dBm is shown here. So basic performance metrics on the tuning range. Going back to our basic functionality, the oscillation frequency determined by V-tune, and we're going to go from some minimum to some maximum. Okay. A sine wave output is shown here. In digital applications, a square wave option is available, and the frequency range and the tuning range are just the maximum and minimum values you need to cover the range the part is capable of. The frequency range shown here, at room temperature, we can actually go a little bit beyond the specified values, so down to 440 megahertz, up to 1070 megahertz. Okay. Note that there is some variation due to temperature. For example, if I come in with a tuning voltage of 9 volts, I could go as low as 775 or as high, as low as 750 or as high as 775. Okay. Methods of tuning used in the different types of oscillators. Some parameter determining frequency must be electrically controlled. For the multivibrator, it's typically going to be the charge and discharge current. For the ring oscillator, it will typically be the gate delay. For the resonant LC oscillator, it's usually going to be voltage controlled of the capacitance in the resonator. For example, of tuning the multivibrator, if I control the reference current with a linear transconductance, then plugging the current expression into the oscillation frequency expression gives me this expression for the oscillation frequency. And if I'm able to make a linear transconductor, I can have a very linear V-tune versus oscillation frequency characteristic. But it turns out, because the multivibrator effectively has a quality factor of 1 or less, the phase noise performance turns out to be very poor, and we're often limited to lower frequencies than we need in most RF applications. Tuning an LC resonator is usually done with a varactor, which makes use of the nonlinear relationship between DC bias and capacitance for a PN junction. If I look at the charge-voltage relationship for the charge in the depletion region of a PN junction, I get a charge-voltage relationship that looks like this. As the reverse bias is increased, more and more charge is uncovered in that depletion region, so I have this relationship between charge and voltage. Defining a linearized capacitance, dQ dV, gives me this type of relationship between the junction capacitance and the applied reverse bias voltage V sub R. And this is characterized by 3 parameters: the zero bias capacitance, the built-in voltage of the PN junction, and the grading coefficient M, which is a property of the doping profile of the junction. So by using this reverse bias capacitance to get a voltage control of capacitance, that will give us voltage control of the oscillation frequency when we use this reverse bias junction as the capacitance in our resonator. So in the example of the Clapp oscillator, this capacitance will realize with the varactor as C3, and the tuning voltage will give us control of the capacitance, and C-tune plugged in for C3 in the frequency of oscillation expression gives us this relationship. This is the tuning that I want. The effect of C1 and C2 also in that capacitance path says that I want to have C1 and C2 much larger than C-tune for the wider tuning range. So there's a trade-off there between the capacitance values and the tuning range. Note also V-tune relative to my VCC, I can extend the tuning range by tuning outside VCC. So that'll give me a larger tuning range. Okay. Some more advanced performance metrics: tuning sensitivity, phase noise, and supply pushing and load pulling. Tuning sensitivity first. Shown here, 30 to 40 megahertz per volt. Tuning sensitivity is just the slope of this characteristic. And because we have the nonlinearity of the capacitance and also a nonlinear relationship between capacitance and frequency, the slope changes depending on where we are in this operating characteristic. So tuning sensitivity is just the change in oscillation frequency as a function of the change in the tuning voltage. And tuning sensitivity is this characteristic shown on these axes, and it ranges from 65 megahertz per volt, the sharpest slope here, and is down by about a factor of 2 in slope at the other end of the tuning range. Okay. Why do we care about this? It depends on the application. In the phase lock loop application, the tuning sensitivity KO appears in the expression for the loop bandwidth of the phase lock loop. The loop bandwidth describes how fast the loop can respond to changes in the input phase or frequency. The loop bandwidth may or may not be critical depending on the application, but it will also affect the gain of the loop and can affect stability. So you need to make sure that even if the loop bandwidth is not a critical factor in your phase lock loop, you need to make sure that the loop will be stable over the range of possible values for this tuning sensitivity. Also, if we're using the phase lock loop for demodulation, linearity of this tuning characteristic can be important, so changes in the tuning sensitivity can be a problem. So looking back where this comes from in the Varactor, the junction capacitance expression is here. Plugging that in for the C in the oscillation frequency gives me this expression for the oscillation frequency in terms of V-tune. The CJ0, the zero bias junction capacitance, is a constant. So all my dependence on the tuning voltage is here. And if for a step junction, this grading coefficient is 1/2. Step junction, where I idealize is going from uniform P doping to uniform N doping. So then this exponent is around 1/4, and there's my nonlinearity. So for a step junction Varactor, I have an inherently nonlinear characteristic between tuning voltage and oscillator frequency. The hyperabrupt junction Varactor has a different doping profile that actually increases the doping density closer to the junction. And in the limiting case, the grading coefficient approaches 2, and 2/2 is about equal to 1, and that's what I need for a linear characteristic. So the hyperabrupt junction Varactor is usually what's used to get a linear characteristic in this tuning range. A disadvantage of the hyperabrupt junction Varactor, it turns out that the quality factor of the diode itself contributes more losses to the resonator. So there's a bit of a trade-off there with phase noise. Okay. Looking at phase noise, looking at the output of the VCO in the frequency domain, where now I've got frequency on this axis and output power on the vertical axis. Okay. Ideally, the output would just be an impulse at the oscillation frequency. Okay. In reality, looking in the frequency domain, at frequencies close in to the carrier, I have this extra unwanted power. And that is phase noise. Okay. And we'll characterize phase noise by the spectral power density relative to the carrier. To see where it affects operation, we can look at the RF system application again. In the frequency domain, when we're multiplying in the time domain, in the frequency domain, we're convolving the local oscillator spectrum with the RF signal that we're trying to down convert to IF. So if our local oscillator has phase noise on it, when we convolve that with the RF, we essentially blur or smear out the spectrum that we down convert to the IF. Okay. So that's one problem. Another problem is if there's a large interferer in an adjacent channel, then the LO phase noise can pick up some power from that adjacent channel, and that can mix in as well. Okay. So to the extent that we deviate from this ideal impulse, we're going to see non-idealities in the IF spectrum that's down converted. In a digital system, the way that phase noise manifests itself is in jitter, where the edges of this clock at the VCO output move around in the time domain. Where does phase noise come from? One way to model phase noise is to look at the thermal noise of the dissipative loss mechanisms in the resonator as white noise sources that are then filtered into a narrow band around the oscillation frequency by the Q of the resonator. Okay. So the transfer function of the LC resonance shapes the spectrum of the white noise. If we make the resonance higher Q, then we're able to push down the spectral density of the noise near the carrier. So a higher Q will give us a lower noise and better phase noise performance. So that's why we prefer a higher Q resonator to something like a multivibrator or a ring oscillator, where there's no energy storage as there is in an LC resonance. So an intuitive way of viewing phase noise, if I imagine starting with an ideal sine wave source, in the time domain, I've got a perfect sine wave of constant frequency, an impulse in the frequency domain. If I then imagine adding wideband noise, in the time domain, I'll see this wideband white noise fuzz added onto my sine wave. In the frequency domain, I'll see the noise floor come up at all frequencies since I'm looking at white noise. Now, if I imagine trying to clean up this sine wave, it's only natural to put it into a narrow band filter around the oscillation frequency I'm trying to pick out. So what that will do is kill most of the noise, but I'm going to have to keep the noise near this carrier, near this oscillation frequency. If I'm filtering white noise is totally random. It's equally likely to be amplitude noise and phase noise displacing zero crossings. So if I take that filtered waveform that's got both amplitude noise and phase noise, put it through a hard limiter, then I'll eliminate the amplitude noise, so half of this power goes away. But the phase noise, I can't do anything about that because it's occurring near the zero crossings, so I'll be left with this shape of the phase noise close into the carrier. And that's the phase noise that I need to get rid of, or I need to minimize by using a higher Q oscillator. How we're going to describe phase noise is in the frequency domain, looking at offset frequency from the carrier, because the filtering is symmetric above and below the carrier, I can look at a single-sided representation, and I'll normalize the noise power spectral density relative to the carrier in dBc, decibels relative to the carrier. For white frequency noise, it turns out the phase noise slope goes as 1 over f squared, so that's a minus 20 dB per decade slope. Other phase noise processes, such as 1 over f noise, will give different slopes to that phase noise characteristic. So looking at the phase noise specifications for this oscillator, if I've got my reference 0 dBc, and I'm looking at an offset frequency of 1 kilohertz from my fundamental 10, 20, 30, 40, 50, 60, 73 dBc. So that's this number at a 1 kilohertz offset. And as we see at higher offset frequencies, as I go out in a factor of 10, from 10 kilohertz, 100 kilohertz, 1 megahertz, I'm going minus 20 dB per decade. And close in, we deviate a little bit from that 20 dB per decade slope due to 1 over F noise. But in practice, when you're limited by white frequency noise in the resonator, the 20 dB per decade slope for phase noise in terms of offset frequency from the carrier is something you'll see. Sources of phase noise in the Clapp oscillator. The tuning path itself, whatever I'm using to generate that tuning voltage, it's going to have some noise associated with it. The Varactor has some losses to it. That will have thermal noise associated. Losses in the resonator in the L and the C. And noise of active devices. The noise of the transistor in this case. So all those noise sources need to be managed to determine the phase noise contribution to the total phase noise performance of the oscillator. The last few parameters we'll look at, supply and load sensitivity. Ideally, the tuning voltage is the only way to change the output frequency. In reality, other factors are involved depending on the specifics of the circuit. Two are the power supply dependence and dependence on the load. Supply pushing, if VCC changes, say VCC decreases, we have a nonlinear relationship between voltage across the Varactor diode and the capacitance. The bias conditions will change a little bit when we change the supply voltage for this device. That's going to change the oscillation amplitude and frequency to some extent. And with a change in those internal signal amplitudes, we're changing the conditions on this nonlinear element, and that will result in some change in the frequency. Load pulling, my output is connected to some kind of load. And to the extent that this load is not matched, there will be some reflection of energy back into the output. That can couple through parasitics in the gain element, which in turn couples into the resonator and can give a change in the oscillation frequency as well. So that's a look at some of the performance parameters for voltage-controlled oscillators. In conclusion, different types of oscillators. For the VCO, the first-order behavior, the tuning voltage controls the output frequency, and we can specify just by the maximum and minimum range of the oscillation frequency and the tuning voltage. Several different types of performance limitations, the linearity of that tuning characteristic, the spectral purity close in for the phase noise. We didn't talk about harmonics, but if those are important for your application, those are specified as well. And also supply and load dependence with the power supply and the output load seen by the oscillator. Different types of VCOs that we've looked at, different architectures, trade frequency range, tuning linearity, and phase noise performance for different applications. So that concludes the first part of the presentation, and I'll now take any questions that you'd like as mediated by our moderator, Pat.
Thanks a lot, John. Great presentation. Lots of compliments already and a lot of questions here, so we'll get through as many as we can.
Certainly.
First question is, for oscillator designs with no frequency reference, how is the frequency accuracy added?
So in the case of an oscillator design with no frequency reference, you're essentially looking at the resonator to provide you the accuracy. So let me find the Clapp oscillator here. So the inductor value and the equivalent capacitance will set the oscillation frequency. And other than controlling those values very well, that's your oscillation frequency. If you need accuracy, you probably would go to a crystal-type resonator or a SAW oscillator, something where the where the accuracy is more precisely determined. The trade-off there, if you make those voltage controlled, then the range is going to be much tighter. So the accuracy versus tuning range is another kind of trade-off you would see if you need a very accurate oscillation.
Okay, great. Next question is, would you discuss the parameters that affect tuning speed across the frequency range?
Tuning speed across the frequency range. So that would be, let's see where we had it here. All right, so the Q of the oscillator is to some extent going to determine how fast it can respond if the parameters of the oscillation change. If I've got a lot of energy stored in this LC, then it's just going to take time to change. Also, the bandwidth of the path from the external tuning voltage to the varactor itself. So there are a couple different factors there, and I believe some VCOs will specify a modulation bandwidth that tells you how fast you can change the tuning.
Okay, next question. Could you comment on the temperature stability characteristics of the oscillators mentioned?
Again, the temperature stability depends on how well the bias condition is stabilized, the temperature dependence of the tuning capacitor. If we go back to the relationship for Varactor tuning, the CJO, the zero bias junction capacitance, is temperature dependent, as is the built-in voltage. So the more your oscillation frequency depends on those characteristics, the more sensitive you're going to be to temperature in the tuning. But all that is folded into the characteristic, the tuning sensitivity characteristic that's reported over temperature. So if you just look at that data, it'll tell you if the oscillator is going to be stable enough. If you're in a phase lock loop application, the loop will compensate if the center frequency of the oscillator changes with temperature. So as long as your tuning range at temperature is able to reach the oscillation frequency of interest, you can tolerate temperature variation.
Okay, we have a lot of questions about the how the Varactor Q factors into the phase noise predictions, and then overall, how do you compute the phase noise capability of a VCO?
Again, looking at the contributors to phase noise, let me find that. Let's see, sources of phase noise. So essentially all of the loss mechanisms are going to contribute white noise that are filtered into the bandwidth of the oscillator, and depending on the bias conditions of the device, the loss mechanisms, the long pole in the tent, if you will, the dominant contributor to phase noise could be anywhere in that system. And again, the number that's reported to you is the sum of all those influences. This shape of the phase noise characteristic will tell you at a particular offset frequency how much spectral density of noise you've got to cope with.
And another phase noise related question. Frequency dividers usually decrease the phase noise. Is that because of the uncertainty in the edge position, or how is that available?
Okay, so the question is about the effect of the frequency divider in the feedback. So if I've got this frequency division in the feedback, in the analogy I like to use in a phase lock loop, it's just like an op-amp negative feedback system, and I have a frequency divider instead of a voltage divider in the feedback. So it reduces the phase noise only because it's reducing the frequency by the same factor. Now, if you have a lousy frequency divider, you can add more phase noise than you need to, but essentially what you're doing with this frequency divider in the feedback is just selecting a subset of edges for the input phase detector to compare to the feedback. So as long as you have a well-designed frequency divider, it shouldn't affect phase noise other than just dividing it because you're reducing the frequency.
Okay. see. Can you talk about what are some of the sources of harmonics?
Sure. The harmonics would come from the method of doing the amplitude limiting, and what we showed earlier with the method of amplitude stabilization in the Clapp oscillator was simply to let the soft clipping of the transconductance as the amplitude grows. If it's a hard clipping, you'll get a lot of harmonics. If it's a soft clipping, the harmonics will start coming in a little bit. So mostly for RF applications, the harmonics are not that big a deal because they're so far out of band. Your IF filter will remove those. If you need to have good harmonic performance for a sine wave output, you need a different method of amplitude stabilization that doesn't rely on clipping, that has some kind of automatic gain control instead.
Okay, and we'll go with one more question to finish it off. Are there other techniques to linearize the varactor rather than using hyperabrupt junction?
Sure. If depending on how advanced you want to get in the tuning signal path, let's see, tuning sensitivity. So the Varactor tuning here is inherently has this nonlinearity to it. If you really believe in your semiconductor physics, you can pre-distort the tuning characteristic to essentially bend the voltage input the other way and cancel it out to some extent. You can't do it precisely. So for the applications where perfect linearity is needed or very good linearity is needed, it's not going to work. But it will buy you certainly a factor of 2, 3, or 4 in straightening out that linearity if you want to go with the step-type junction or something with a higher Q varactor. Okay,
great. Sorry if we didn't get to your question today. We had a huge number of questions, probably one of the highest number I've seen. John, I'd like to thank you for an excellent presentation. We got a few comments that this was very well done. And I'd like to thank our sponsor today, Mini Circuits, for the webinar, and you can visit their website for more information on all their devices. Thank you very much for attending today.
Thank you.